Welcome back to Calculus 1. We're still in Chapter 1, Derivatives and Limits. We're in Section 1. We're looking at example number 2. This is the video explanation. The solution to this problem, which is given in the book, is 12 meters per second. So let's go ahead and see how we get that value. So here's the question again. What we want to know is what is the instantaneous. So we want the instantaneous velocity, or how fast the bus is going at exactly 3 seconds. So in the previous problem, we looked for what was the average velocity. Okay, and before we calculated slopes of secant lines, now we're looking at the slope of the tangent line. And that's that that instantaneous velocity. So let's go ahead and graph that guy out again. Now, we're really interested at 3. And before we looked at values like 4 and 3.1 and 3.001 or whatever it happened to be. Here, we don't know how far we're going to go out. We're just going to call it change x, or change of x. And of course, 3 is x sub naught, and then the question mark is x. So again, what we don't know is what is the x value that we're traveling to. So I called it question mark here. All we do know is what x sub naught is, and that's 3. And x sub naught, remember, is the starting value, okay? So, in general, our average velocity is going to be delta y over delta x. Okay? So let's go ahead and just take a look at that average velocity. And so this guy right here has got a height of 3, and this guy right here, we don't know what its height's at. Okay, so f of whatever that thing is, so f of question mark. We're going to fill that in right now. So really the question becomes, how do we find that question mark? Well, here's what we know. We know we started at 3 and we went over a distance of delta x. So this guy must be at 3 plus whatever delta x was. If we went over by 1, then it was 4. If we went over by 0.1, it was 3.1. So this guy up here must be the function evaluated at 3 plus delta x. Now we can go ahead and we can compute our average velocity, which will change into our instantaneous velocity once delta x goes towards 0. So we've got f of 3 plus delta x minus f at 3, and that's our change in our y value over there. That's what we've got. And so we want to go ahead and divide that by the change in the x's. Okay, so it's 3 plus delta x minus 3, which of course is just delta x. So again, we've got f at 3 plus delta x minus f at 3, and we need to divide that guy by delta x. Now, what we need to be able to do is simplify that numerator. So that's what we're going to do here. And this just takes a little bit of algebra. So the first thing we're going to ask is, what is f at 3 plus delta x? And then we'll ask, what is f at 3? And once we get those two, we can fill them in and solve this problem. So f at 3 plus delta x. Well, remember the original function was 2 times x squared, right? So since our x value is 3 plus delta x, we'll plug that guy in there. So again, just if you look at that, our original function was 2 times x squared. So let me just underline that guy right there. That's what we're using down here. And we're using that function notation from the preliminaries. So this is 2 times, now I've got to take 3 plus delta x and multiply it by itself. Do not distribute the exponent. It doesn't work like that, right? You need to go ahead and FOIL this guy out. So it's 9 plus 3 times delta x plus another 3 times delta x plus delta x times delta x, which is delta x squared. So this is going to be 2 times 9 plus 6 delta x's plus delta x squared. And so now we've got 2 times 9, which is 18, plus 12 delta x plus 2 delta x's squared. That is f at 3 plus delta x. Now we need f at 3. Let's grab green here, make it a different color. So 2 times, again, plug in 3, so 2 times 3 squared. That's going to be 2 times 9, which we figured out in the last videos was 18. So again, remember what we wanted to find. We wanted to compute the following. We wanted f at 3 plus delta x minus f at 3 over delta x. Well, we've got some of these values here, right? We know that this guy right here is f at 3 plus delta x, and we know this guy over here in the green is f at 3. So let's plug those values in since we know they're equivalent. So we get our 18 plus our 12 delta x plus 2 times delta x squared minus 18, because we have to subtract off f at 3. And of course, that's divided by delta x. So what cancels here? Well, the 18s cancel out, and we're left with 12 times delta x plus 2 delta x's squared, and that is over delta x. Now we're going to factor out a delta x and divide, of course, by our delta x, and those guys cancel as well. And so what are we left with? We're left with just 12 plus 2 delta x. Now if you go back and you were to plug in those delta x values from the previous problems, you would see that that would give you your solution. And the important part here is as delta x becomes very small, so as our time values become super close together, 12 plus delta x approaches just 12. The delta x drops out. And so the instantaneous velocity is 12 meters per second. So that's our instantaneous rate of change. And since we're looking at velocity in this problem, that's our instantaneous velocity.